investigator on the DARPA-funded SafeDocs research program and one of the two project leaders of ISO 32000, which is the core PDF standard, so I have unique knowledge and experience about this file format. Today I'm here to present the Arlington PDF model, the first vendor-neutral, open-source, specification-derived, machine and human-readable definition of PDF. This talk is just a taster of what is possible with a formal model of PDF, and I won't have time to go into all the details. Everything is open source and freely available, so feel free to explore yourself, comment, or even contribute. Let's begin with thinking about the PDF specification. This defines the PDF file format in a largely implementation-independent way. This allows vendors to innovate with their implementations, but also to make mistakes. It is without doubt a highly complex document. ISO 32000 Part 2 2020 is 1,000 pages with over 70 normative references. That's a lot of reading. It's written in English prose, so if the nuances of English are not your strength, you can struggle to understand clearly and precisely what is meant. Of course, over the 25 years of the format, numerous errors have crept in, including errors of omission. There are ambiguities and self-contradictions in the spec, unstated assumptions, and various other issues. All this leads to differing understanding, differing interpretations, and thus non-interoperable implementations. So what can we do that will give us an unambiguous common understanding to every developer needing to code and comply with the PDF file format spec? Well, we can convert it to a machine-readable definition, and this is what the Arlington PDF model is. So before we deep dive into the Arlington model itself, what might you do with a model of PDF? You could obviously use it for code and parser generation, and in the case of SafeDocs, these are provably correct parsers backed by formal methods. You could use it to generate PDF writer software, ensuring that the PDFs created are always valid according to the spec. We can obviously use it to correct the specification itself. Through the creation of the Arlington model, we have already identified and fixed numerous issues, and we will continue to work towards a better, unambiguous specification. A model can be used as the basis for detailed documentation for PDF technology, since very few PDF technologies provide many details about what they do and do not support. A PDF model can be used for test case generation, code coverage, as an aid to code review of PDF-related software, ensuring better quality and compliant PDF technology. A model could be used to assist in the due diligence when acquiring third-party PDF software, whether it be OSS or commercial. A model could be used to check extant PDFs to find deviations, malformations, and errors according to the spec. And in digital forensics, you can use the model to diagnose, analyze, and dissect a PDF or just part of a PDF. And the list goes on. Hopefully you can see a few things here that are of interest to you. Let's begin thinking about the data itself now that goes into a model. When we look at a typical table in ISO 32000, you can begin to see repetitive information which can be captured as fields into a structured format. We have the key name or array index, we have the permitted type or types, we have information regarding whether it is optional, required, whether it has to be a direct object or has to be an indirect reference. We have information of when the individual key was introduced and optionally when it was deprecated. We might have permitted values or some range of values or a default value. And if the data type is a dictionary, an array, or a stream, it will also tell us what kind or kinds, plural, of dictionary, array, or stream are allowed. And of course, there may be many other statements describing data consistency rules, relationships to other keys, etc. The spec has been handwritten over the 25 years or so that the PDF spec has existed, so the repeatability of this data varies throughout the 1,000 pages of ISO 32000. But this is the data that has been captured into the structured format that is the Arlington PDF model. Let's have a quick look now at how the Arlington model itself is encoded. Each data object has an identical structure and is the full and complete definition of a single PDF dictionary, array, stream, or map object. By map object, I mean any object that has arbitrary key names or array elements, such as resources subdictionaries. There are always the 12 structured data fields shown here that map directly to the data points in the tables of the PDF spec that we just saw. To express the many shall and shall not data integrity requirements from the spec, the Arlington model uses custom predicate statements. Think of these as assertion of facts. We will look at these more closely later. Such data or integrity relationships express precisely what is stated in the PDF specification, and you can see a few examples here at the bottom of this slide. So hopefully now you understand a little bit more about what the model is. The Arlington PDF model is the first fully open source, extensible, specification derived, meaning it's been directly created from ISO 32000 Part 2 2020, structured data, machine and human readable, vendor and implementation neutral, meaning it's not correlated with any specific implementation, comprehensive definition of every PDF object in the PDF document object model. Every key in every dictionary and stream and every array element and every array is formally defined. You can find the freely available Arlington PDF model in GitHub under the PDF Association's account. The model covers the vast bulk of the pages in ISO 32000 with all the tables of keys, their types and permitted values, conditions when they were required, what version they were introduced in, if they've been deprecated, etc. The model enables us to look inside the PDF file format in a reliable, unambiguous manner and see how all the cogs interlock to make portable, interoperable documents, hence our logo. And why is it called Arlington, you ask? Well, the other PDF Association assets, such as test suites, have been historically named after the location where they were established. For example, the Matterhorn Protocol, ISATOR Test Suite, etc. The creation of this PDF model was supported by the DARPA funding through the SafeDocs research program, and the DARPA headquarters is in Arlington, USA. While I appreciate it doesn't yet cover file structure and layout, such as cross-reference tables and incremental updates, the lexical analysis rules, or definitions of operators and operands and content streams, there is nothing stopping this from being added to the model in the future. The Arlington PDF model is text-based in a collection of tab-separated value files, or TSV files. Thus it is both human and machine readable. There is one TSV file for each PDF object, dictionary, array, stream, map, etc. And every TSV file has that identical structure we just saw. There are currently 515 individual TSV files comprising the model for PDF 2.0, with earlier PDF versions having less objects. TSV data is not overly verbose, and nor does it require any specialist knowledge to read or understand. TSV files are trivial to process regardless of what programming language or platform you use. They are also directly viewable in GitHub in a user-friendly way. With individual TSV files, it is easy to diff to see changes at an object level in GitHub or in your console, and you can make patches at an object level, which provides the capability to extend the model in whatever direction you wish. For example, adding proprietary keys to dictionaries that your implementation may support. TSV files are trivial to combine into a single large file or convert to other formats such as XML, JSON, transcode to custom domain-specific languages, or import into more complex binary formats such as SQL or into spreadsheets, subject to the size constraints of the model. TSV data is truly easy to work with. So what's possible with the Arlington model? In one word, lots. You can use a model without any coding at all, in a no-code approach. You can use just a few lines and use a low-code approach, or if you are a developer, you can use your programming language of choice. As an example, you can convert the Arlington TSV file sets using the scripts and applications that are included to convert to XML. And then with the supplied XML schema for Arlington, you can use XPath to query the model. The Java proof of concept application we provide can also convert the TSV datasets to XML for you, as well as demonstrate how to use XPath queries in just a few lines of Java. If you prefer JSON, you can use the JQ command to query the model, and a provided Python script will convert Arlington to JSON for you. If you prefer big data tools, then you can combine to a single monolithic TSV data file and use utilities such as DataMash, the eBay TSV utilities, or the Python modules such as Pandas. Or you can just stick with the simple basic model as we provide and use simple Linux commands such as grep, cut, etc. A proof of concept application has also been developed in C++ with much more capability, including being able to formally compare the model against PDF files, report conformance issues, and to validate the model for consistency and compare against an alternative proprietary model. A Python proof of concept can also do similar things. So let's get started. The rest of this presentation will be demonstrations of what is possible with the Arlington model using these various tools. So what do you get when you clone from GitHub? Here is an Ubuntu shell showing the folder structure from GitHub, with the core data model being in the TSV folder. The XML data is obviously in the XML folder. Test Grammar is a C++ proof of concept app that can validate any Arlington Model TSV file set for syntax errors and self-consistency. GCXML is the Java proof of concept app that can create PDF version specific subsets from the latest TSV datasets, create the XML data, and run a few research-related queries using the XML data and XPath queries. The scripts folder contains Python scripts and a sample Jupyter notebook that I will walk through soon. The 3D Visualize folder has JSON data supporting 3D and VR visualizations of the Arlington PDF model that is hosted at safedocs.pdfa.org. Let's now look more closely at the model data itself. Beneath the TSV folder are subfolders containing an Arlington TSV model for each specific PDF version. I'm going to stick with the earliest PDF versions as these models are slightly smaller and fit on the screen better. Note that the Arlington model does not yet contain all the information from all the past PDF specs, as it was primarily used to prove that modeling of obsoleted PDF features was possible. So the TSV1 folder has the model for PDF1, which comprises 47 PDF objects. The file names are generally recognizable by anyone with passing familiarity of the PDF file format. The TSV 1.1 folder has a similar but larger model for PDF 1.1. It has 84 PDF objects. Again, the file name should be familiar, but the contents of these files may have changed. For example, new keys and objects introduced in PDF 1.1 will have been added. If I then look at the master model in the TSV latest folder, I can see that there are 515 unique PDF objects, so it is a much larger model. If I then count all the rows in all the TSV files and then subtract the number of files, since each file has a header row, I get the total number of keys and array entries that go to make up PDF. Remember these numbers: 515 files and 3,544 rows. Remembering that TSV files are text files, we can list a file to the screen, and note also that the default tab settings rarely work, but we can use the Linux tabs command to set something appropriate to the screen width. Or far simpler, we can use the eBay TSV utilities TSV pretty command. Here is the content of the dictionary object, which defines a device-independent RGB dictionary with white point, black point, gamma, and matrix keys. You can recognize the column names from what I showed a few slides ago. If I then do the same thing for the whitepoints.tsv file, I can see that it is an array because all the key names are just zero-based integers. PDF does not define any purely numeric key names. You can also see here some of the predicates, fn:/since version and fn:/eval. Using some basic Linux commands, I can extract all the types used in PDF. I can use the cut command to select the second field. I can then pipe this through sort and unique to get all the unique combination of types used in PDF. Notice that the Arlington grammar for the types field is an alphabetically sorted list of predefined types separated by semicolons. Again, you can also see a predicate statement being used here, indicating that in PDF 1.3, a dictionary was added as a valid type for one or more keys and one or more objects. Predicates always begin fn:/ and the name of the predicate with operands in brackets. You should be able to appreciate how this predicate could either expand to dictionary for PDF 1.3 and later, or reduce to nothing for PDF 1.0 to 1.2 inclusive. Knowing things are semicolon separated, we can use a bit of sed magic to see the full set of Arlington types as well as all the predicates in use. You can see from this list that Arlington includes an extended set of types such as bitmask, date, matrix, rectangle, and name and number trees, as this further allows other assertions or predicates to be made. It's not so easy looking at these Linux command prompts, so let's move across to something nicer and use Jupyter. Jupyter notebooks are commonly used in big data and machine learning. You can think of them as a record of an interactive Python session. I previously installed Jupyter via pip3 into my Python 3 installation and began by running the Jupyter notebook command in a console from the scripts folder in the GitHub clone of Arlington. For me, this is a Windows 10 command window. This will then open a page in your browser. Click on the arlington.ipynb file and you should see this screen. As described here, this demonstration has taken the individual TSV files from the TSV latest folder and combined them all into a single very large TSV file I call pandas.tsv. This process adds a new column as the leftmost field called object and is the TSV file name from Arlington. These first two cells shown here import the required Python modules and then load this pandas TSV file into the pandas data frame. Pressing Control Enter or clicking Run makes a cell run and will move you on to the next cell. So we will move to cell 3, which will just dump data for the first few rows. Cell 4 does the same for the end of the data. Okay, that looks very familiar and is instantly understandable. And notice that last row number, 3543. With row numbering starting at 0, this correlates with the 3544 we saw a few slides back. A few things to note. Arlington defines two special objects, _universal array and _universal dictionary, which represent arbitrary PDF and array dictionaries, respectively, with no constraints. You can see here an asterisk as a key name, which means a wildcard, so anything will match. The Arlington grammar also supports flexible matching for repeating sequences of array elements using a similar syntax. And as previously mentioned, for multi-type entries, Arlington always uses a semicolon separator in the types field. So how many keys and array elements does Arlington define across the 515 objects in the latest model? Let's check, and then also let's look at the types that Pandas is using and the individual columns of data. Okay, 3,544 rows of data for PDF2. That matches what we saw in the Linux console and what we saw just a few cells back. And we can see in the output for cell 6 that each column of our TSV data is stored as a string. And in the output for cell 7, the column titles from the TSV header row that we are using. So let's now look at the new object column that was added when I merged a full set of Arlington TSV files into this single monolithic TSV. At the Linux command prompt we saw earlier, this would be the file name, but here in Pandas, it is a separate field in our data frame. And how many objects do we have? We can access the columns of data simply by using the column title. And to work out the number of unique objects, we can simply use the pandas unique function, which is the same as counting the number of TSV files back in the Linux command prompt. In the output for cell 8, we can see the values in the object column of the pandas data frame. These are the TSV file names. In cell 9, the number of unique objects is 515, which is exactly what we expected for the latest Arlington PDF model. And it's what we saw in the Linux command prompt earlier. I hope by now you're beginning to appreciate how easy it is to access and use this PDF model. It's only a matter of preference whether you use the Linux shell commands or something like Python in this Jupyter notebook, or even some more advanced programming in C++ or Java. But let's continue here in Jupyter. Okay, we have 515 unique PDF objects exactly as we expected. And using semicolons, we can also decompose the type column into an array object if we wanted to do further processing. Let's now find objects that have a subtype key. Okay, 80 PDF objects have a subtype key. That was much faster than trying to work that out by trolling through ISO 32000 Part 2. Let's make it a bit harder. What about objects that have an ASCII string key or array element and where it is stated as being required? That's a fairly easy query to read. And bingo, we get 7 hits, 6 objects, and all the relevant details are at our fingertips. Quick and easy. Let's do something now that would be effectively impossible from reading ISO 32000. Let's get a rough feel for how many keys or array elements were introduced in each PDF version. And let's view that as a histogram using the matplotlib Python module. Okay, and here it is. Technically, I should have set up proper bin sizes, etc., etc. But for purposes of this demo, you can see how easy it is to explore the PDF file format. So let's conduct a bit more of a forensic examination, such as you might get from a customer who is unable to share a full PDF with you. Suppose I have a PDF fragment where all I know is that the objects 52 and 53 are key as an array, and that N, P, T, and V keys also exist. But I have no idea whether these are streams or dictionaries or basic types such as integers, names, etc. So what am I looking at? The first thing we would do is to slice our model based on these key names. Then I know which objects can have each of these keys. But I need to go one step further and find the intersection of those objects because we want all those keys in a single object. I can use pandas inner join merge to do this as shown in cell 17. And the answer is bead and bead first, which is really a bead dictionary with additional constraints for being first in a series, or a target dictionary. But target shows me that the R key is a name, whereas in my fragment, it is a 4-element array, or likely a rectangle. Thus, the answer is that the fragments show bead dictionaries. So I can now head off to ISO 32000 and read up on bead dictionaries to solve whatever issue is being reported. So let's now consider whether we can think about our implementation and whether it's correctly supporting inheritance. We get a subset of the Arlington PDF model for which the inheritable column is true. That's 68 keys that are formally defined to have inheritance of some kind in PDF2 as defined by ISO 32000 Part 2 2020. Let's narrow it down to inheritable keys that are also required by subsetting further based on the required column. And we get 12 hits. Your gut might say, that doesn't seem enough. I thought there were more required inheritable keys in the page object. Let's investigate a little bit further. Okay, that's super easy with a one-liner as shown in cell 21. But hang on, what's that HID key, the last row of the table, or row 2638 of the full data frame? That's not in ISO 32000. Let's get the full data for that specific row. I could have got it via the index 2638, but using this longhand approach is far more descriptive and understandable. Okay, here it is. It's an old key introduced in PDF 1.1 and that was then deprecated or obsoleted in PDF 1.3. But what about all the other box keys in the page object? Because we are working with strings, we can look for keys that have the string box. And then we remember that these other boxes are not required and that they get their default value from other boxes. The @keyname syntax in Arlington is the way that we express a value of key. So the default value of the bleed box is the value of crop box. This Jupyter notebook is in GitHub in the scripts folder for you to play with in your own time. I hope from this quick walkthrough you can see the power that a PDF model can have. Although I have used Jupyter, I could have done exactly the same thing using Linux shell commands such as grep and cut and so forth, using the eBay TSV utilities at the command prompt, the XML lint tool with the XPath option and the XML version of Arlington, or the JQ tool with the JSON version of Arlington. Effectively, the choice is yours. To finish, I'd like to share what the C++ proof of concept test granner application can identify. This app traverses the object DOM in a PDF file and reports deviations from the spec as it is encoded in the Arlington model. The app is only proof of concept and it's not perfect, but it is able to identify many different kinds of errors and warnings. Anyone involved in PDF expects that real-world PDF files can and will occasionally have variations from the official spec due to either malformations or proprietary extensions. The first warning message shown here is one such extension using a proper second-class name. These other error messages shown here are typical of the differences we encountered in a corpus of over 200,000 PDFs. Spelling mistakes and capitalization errors in key names or using an incorrect data type will not be processed by consuming software as the created software probably intended. Of course, it is also very disappointing how such trivial mistakes are not detected and corrected before the PDF writer software was released, if only they had a model to compare against. What you do about such errors in your technology is clearly outside the scope of ISO 32000. As the Arlington PDF model is a specification derived, such malforms will never be added to the official model. But if your organization decided that accepting these malforms was necessary, then you could easily create a set of TSV patches against the appropriate TSV files to extend the official Arlington model, which also provides detailed documentation of exactly which malformations you support without having to troll through code. Note that I'm not encouraging anyone to do this, but just illustrating how the text-based per-object TSV Arlington model has been designed to be both flexible and extensible. This last error message is from a previous version of the Arlington PDF model, and it had an extremely high occurrence rate in our corpus. When we examined the PDFs in more detail, it was apparent that many well-known and widely used creative applications were still creating such files today. This issue was raised to the ISO committee responsible for PDF, and where representatives from many vendors participate, and it was agreed that the PDF specification was indeed too strict. As a result, the change shown here was introduced and published in the latest PDF 2.0 spec in December 2020 as part of ISO 32000 Part 2 2020. It's an adjustment to the specification to reflect real-world data, or the de facto specification that many parsers have to implement, and the current Arlington PDF model has since been updated to reflect this specification change. So to conclude, the Arlington PDF model is the first open access, vendor and implementation neutral, specification derived, machine and human readable, comprehensive definition of every PDF object in the PDF DOM. It does not replace the PDF spec, but sits beside it and reflects a stable ground truth that both machines and humans can unambiguously consume. It is a set of lightweight, text-based TSV files with 12 columns of data and a set of custom predicates that directly express wording from the spec. It is platform and language agnostic and can be used directly as is with the no-code approach, as I briefly demonstrated, or use a low-code approach with scripting languages such as Python and the Jupyter notebook I demonstrated. Or you can build on our larger proof of concept implementations in Java, Python, or C++. We have validated the Arlington PDF model against a proprietary model as well as a large corpus of extant data. In this process, we discovered many issues in PDF, with several being fixed in the December 2020 edition of ISO 32000 Part 2. Of course, there is always room for expansion and improvement, both in the expressiveness of the predicates about object relationships, as well as expanding the model's scope. This might include file layout, lexical rules, nested formats, legacy PDF specifications, or extensions for specific research or industrial use cases. There are many possibilities. Being text-based, a set of diffs or patches can be applied to the evolving model if you wish to augment the model for your own use using a private sidecar approach. Going forward, we hope that everyone in the industry will adopt the Arlington model to improve the quality and interoperability of PDF software. Thanks for watching. I can now take any questions.
All right, wow, thanks, Peter, for that. Let's go into, now it's time for some questions. You can still submit questions to Peter through the questions pane in your attendee control panel. And let me see what we have here. So here's a question, Peter. Is Arlington only for PDF 2.0 because it's from ISO 32000-2, or is it, is it only about the PDF 2.0 specification?
So no, it's not. As you saw, we have data sets for each of the earlier PDF versions. At the moment, the data in those earlier versions has been extracted from ISO 32000, which of course has many, or the large majority of keys and data points from those early specs. But we haven't actually gone back through the specs, those old specs, and found everything that was removed many years ago. And that example I showed with the hid key, the hidden key, where it was removed in PDF 1.3, that was just a small sample that was added to prove the concept of adding older keys. So it's perfectly valid for PDF 1.7, 1.6, 1.5, and 1.4, so the common versions that we see every day. So hopefully that answers the question.
Yep. So why are there so many more files in Arlington than there are tables in the PDF spec, given the breakdown of TSVs as you described it?
That's a good question. It's because in PDF, in the spec, we're used to sort of encountering a table and then reading a key. But what we sort of forget is that sometimes the description of what that key is, if it's a dictionary, might actually be in that cell on the right-hand side. The PDF spec, as I showed, has 3 columns for the key name, the type, and then a description. And sometimes the actual description of an entire PDF object is in that description cell. And I also showed the example with the bead and the bead first dictionary. Sometimes we create additional objects so we can encode additional constraints. So for example, in the case of bead first, there are additional rules regarding the first dictionary in that, I think it's a linked list of dictionaries, and we want to capture that. And it's a little bit easier in the grammar that we have, the custom predicates, to explain that using a separate file definition rather than trying to confuse the generic bead dictionary. So those are sort of the two main reasons why we end up with 515 TSV files, but there's somewhere in the order of 300 to 400 tables in the PDF spec.
Mm-hmm.
Hopefully that makes sense.
Mm-hmm. So so does Arlington define everything from the PDF specification, or what is it broadly speaking that it leaves out? And that
Okay, another good
lines up
question.
with another question. Another question we have is somebody points out that it would be nice to have the text from the specification in the model as well. Of course, there are copyright limitations, but back to you.
Well, maybe that we talk about that one first, and that'll help answer the second one. So first of all, obviously, at the moment, Arlington contains almost no text directly from the spec. In some cases, there is the 12th column is a notes field, and occasionally there is a sentence in there. That tends to be in a case where we haven't yet encoded whatever that requirement is in a custom predicate that can be machine read. So free text, I'm not thinking of as being machine readable. A human can easily understand it, but a machine will struggle with it. So that's what's in the notes field. The rest of the spec, so the spec really contains multiple things. So the part that I've captured here is the file format portion, and processor requirements are not captured. We don't have the formulas for all the sort of complicated transparency stuff. We don't have a lot of descriptions of how annotations are supposed to look and how squiggly line outlines are supposed to look and all that kind of stuff. So there's still a lot that you need in the spec in order to create, if you like, an implementation. What we're providing here, I think, is a database. I don't want to call it a database. I prefer to call it a model, but structured data that you can use to prove at least that you're reading all the keys correctly, or that you're got all the spelling correct in the key names. I mean, it's very unfortunate when we look at files and find these really trivial mistakes, and then all the PDF consumers out there, being the viewers and so on, then have to struggle with that. So those are the main reasons that you can't use the model without the spec. We don't have the processor requirements, and it's really just the file format side of things that have been captured.
Mm-hmm. So here's a question. Could you shed some light into some inconsistencies you found in the specification using Arlington? Obviously, you talked about some of the typos and so on, but are there other more systematic, if you will, inconsistencies?
Yes, so one of there are a couple of examples I can think of off the top of my head. So one of them is I did mention that the model contains the wording from the spec. We've been very careful not to, and we did have a discussion in the early days of the model whether we wanted to actually make the predicate something like JavaScript or a Lua or scripting language or some other scripting language. But that involves interpreting the spec. So the example I give is the word meaningful. In the PDF spec, that occurs roughly 50 times. We say this key is only meaningful if, and some condition. Now, what meaningful means will depend on whether you're, first of all, a PDF reader or a PDF writer. And maybe how you interpret that also will depend on, your understanding of other parts of the spec. So the way Arlington models that is we have a predicate called is meaningful, and we just put the condition that the meaningful statement out of the spec has in there. And we don't attempt to define it any further. Then, with your implementation and how you've interpreted the word meaningful, you can construct your code definition around that or get a better idea of it. So we've been very careful not to reduce the PDF spec based on our own internal biases or assumptions. So that's probably the best example. Other errors have been inconsistencies. We found missing keys. We found incorrect version numbers. We've found, I think, some types that said something could be an array, but didn't actually then give us the formal definition of the array, or where the array definition didn't make sense. So there's been a lot of, I guess, the finer points, because previously, and as I noted in the presentation, the spec's been written by hand by humans and read by humans. And obviously at 1,000 pages, that's a lot of reading, a lot of sort of neural workload in our minds as we review it, trying to think, yep, that makes sense, that doesn't make sense. But this is a way of almost compiling the spec, at least the file format parts of the spec, and then checking it for some kind of what I call self-consistency or validity.
Mm-hmm.
So hopefully that answers that question.
Yeah. So another questioner asks, another attendee asks, how mature is this model? do you expect more changes, due to ambiguities revealed in the specifications, or is it more on that the model you expect it to expand into other areas such as lexing rather than maturing in terms of the data it's already handling?
So the model's been around roughly for about a year now, although only a few people have been working with it. It's used heavily within SafeDocs. So I would sort of say it's somewhere in the order of, and I don't like to give percentages, but if I have to, it's sort of, an 80-20 rule. It's at least 80% mature. It's not to say there's no mistakes in it. That's why we run it against the files to try and find mistakes. And we certainly did have typing mistakes and other errors we introduced through the process of creation. I think it is a mature model. It will definitely expand in both its breadth and its depth. By breadth, I mean I would like to go back to those earlier PDF specifications, especially ISO 32000 Part 1, and make sure that anything that was in there that was removed in PDF 2 was actually added to the model, so it's fully reflective of the ISO specs. And I also expect that we'll expand the predicate models as we look at things more deeply. For example, with rectangles and matrices, we don't yet have too many predicates that look and sort of say, well, can I have, can this rectangle be a 0 height rectangle or a 0 width rectangle? In the spec, it doesn't say very much about that at all. In actual fact, it says almost nothing. So I think there's a lot of opportunity to go through the model and really look at the nitty-gritty details. Programmers, implementers will have already had to do that because that's what programmers have to do. They have to think about, well, if I'm going to divide this by the height of the rectangle and that height is 0, then, it's a divide by 0. So many people will have, I guess, opinions about whether, a particular rectangle in the PDF file format shall or shall not be 0 or cannot be 0. So I would like to try and capture that much greater level of detail that's actually, technically speaking, not in the spec at the moment.
Mm-hmm.
But yeah, the vast majority of it's there. When you run our CESMA Plus test application, which was shown on the sort of next to last slide, you can get some false messages out at the moment, and we appreciate that. But I think as we refine the model, those false messages will reduce. But it gives you a very good idea about sort of how, according to spec, a PDF file can be.
Yep. It's just got first a comment. Is there, I guess more of a question really, or clarification. Is there a reference to does the model include references to the place in which given elements are defined in the specification?
No, it doesn't actually, and that's a really good point. No, it doesn't. And that is probably one of the limitations of the model. As I said, when we started, we thought that would be a good thing to do, but we fairly quickly found that there were so many places where the requirements weren't always, in the table, for example. Sometimes they're in prose outside the table. Sometimes they're in other sections, which will make a comment about something that probably should have been elsewhere in the spec. And I guess this comes down to the fact that the spec has been written over, many, many years. PDF is a great format, been around for many years, but it also means the documents probably had, a multitude of authors. So it's not as clean as you might think. Many keys have requirements that are pulled from multiple places in the spec, so it's not just one place. So in summary, the answer is no, but it's not as easy to do that. You would have to have multiple places to anchor specific requirements.
Yep, you're just going to have to read them, have them side by side to that extent.
Well, what would be better would be to actually, I think, personal opinion here, not the association's opinion, would be to switch to having a more machine-readable spec, and then the text associated with the model, rather than trying to put the model associated with the text.
Right.
And then that would also avoid things like duplicated requirements. We certainly found a few of those where it says, one thing at the front of the spec, one thing 100 pages later on, and they contradict each other. So, yeah. Personal opinion.
Well, actually, that's a great lead into I think the last question we have time for today, which is, what did you do with inconsistencies in the spec? Did you use the version from the specification, or how did you resolve that? Were there lists? Did you identify differences between the official spec and the model in any way?
Yes, we did. In some cases, we went back to Adobe, and I do want to give a shout out to Adobe and to Leonard in particular for supporting questions. But at the moment, if we find these things, I'm raising them through the PDF Association's PDF Issues GitHub repo. If you visit that repo, you will see some of the issues that we've raised. Some of them are more systemic. For example, the meaningful issue that I mentioned a few minutes ago, that's there. The fact that some integer keys do not have any range of values, yet they would, when you read it, have a hint at maybe, whether the value 0 is meaningful or not meaningful, or valid or not valid. So those are raised in the issues repository, and we discuss those openly in the public in GitHub, and then the PDF TWG in the association makes an industry recommendation so that implementers at least can move forward and code up something that we generally think ISO would accept. And coming into the future meetings, we will be submitting a number of these industry approved resolutions to ISO, and hopefully then getting approval for these corrections, and we'll have to work out exactly how they get published and disseminated to developers.